So I'm presenting here on behalf of my colleague Lou, who cannot be with us on this year's conference, but I promise to do my best to present her work here. So let's talk about temperature prediction for room control. First question is, why? Why care about that? Well, there were dozens of publications out there stating that with an advanced control scheme like model predictive control, you can achieve significant energy savings, which means 10, 20, up to 30%, depending on your system under consideration. But there are a few obstacles which have to be avoided. And if you want to deploy model predictive control, you need, of course, predictions for that. Model predictive control needs predictions for disturbances and states of the system, and room temperature will typically be one of the states of your model that has been used. So we need a prediction for the room temperature that should be accurate, should be computationally efficient, and of course portable, because we don't want to configure it for a single room with manual effort, but we want to deploy it to probably a whole building with just one click, and therefore we also need this portability. For the prediction itself, we use Gaussian processes because they have some clear benefits. First one is that the math is quite straightforward. In principle, it is like sampling from a multivariate Gaussian distribution conditioned on your training data set. Second benefit is that you directly get kind of error estimate for free in terms of these confidence intervals. That is, if you are close to your training data, then the Gaussian processes say that this error band is quite tight, and it widens up if you leave your region of known data. And that has another benefit if you consider, for example, kind of hybrid modeling, where you have this data-driven model combined with physical models. You see that the Gaussian process is parameterized by two values, the mean value and the covariance matrix, which is determined by the kernel function, but the mean can be set, or is typically set to 0, which means if you are in a region where no data is known in the training data set, then the Gaussian process outputs, goes back to its mean value, which means it outputs 0, and combined with the physical model, it automatically means if you want to extrapolate in a region where no data is known, automatically these physical equations get more importance. So these are some clear benefits speaking for Gaussian processes. However, as always, this comes at a cost, and that is there is no recursive formulation of Gaussian processes, like for example in Kalman filters, which means it's not possible to update your priors if new data arrives in the training data, or do some simple retraining like in neural networks. But instead, in Gaussian processes, you have to train from scratch if new data arrives in your training data. And the drawback here is that it has cubic time complexity, mainly due to inversion of an n times n matrix, where n is the size of the training data, and therefore that is not feasible for large data sets. To cope with that, there are several possibilities. One is to sparse out your training data, like making an educated guess which data is important and which is not, and then to drop that unimportant data to get a smaller training data set, but still incorporating all the information contents present in the data. We followed another approach here, the so-called locally growing GPs, log GPs, where you have only GPs of fixed size, for example 400 data points, and if you exceed that limit, you split up the Gaussian processes into two and eventually build up a tree like that, where you have the Gaussian process as leaf nodes, and along the edges you have an allocation rule which assigns for each data point a kind of weight or probability that you go down this edge to this Gaussian process then. Nice thing is that these probabilities are not discrete, 0 or 1, but they have continuous values so that you have a kind of overlap between these Gaussian processes, so that you have a smooth transition if you go from one Gaussian process to the other and don't have these hard cuts to decide which Gaussian process then to use. Another issue was the portability. So we want to deploy it on a whole building with just one click. So we don't want to configure it manually, but we want to have an automated way to deploy these Gaussian processes to different rooms. and therefore we use a knowledge graph from the building where we have the room and associated with it all field actuators and all sensors, so we can query ourselves when we want to deploy a Gaussian process which actors and sensors are relevant for that zone. So back to that slide, accuracy and computational efficiency we obtain through the log-GP approach. We have the semantic-based framework for the portability, and what we need is input feature selection. We come to that in a minute. The workflow looks like that. Then first step is to acquire the metadata for the room, so querying the knowledge graph about the sensors we have present for that room. Then with that we go to our time series database to query the training data relevant for that Gaussian process of that zone. And finally we train then this log-GP model and obtain the predictions of the zone temperature. So coming to a case study, we did at our site, we have different zones in that floor with different properties. We have some rooms with only internal walls. We have some rooms with external walls, with a high window fraction, with a low window fraction. We have variable airflow dampers within each zone. Some have a radiator, some have a reheater. So we have a wide variety of different zones where we test our system. And question that I omitted up to now was is sensitivity analysis. Which inputs are important for the Gaussian process and which are maybe neglectable? And therefore we have these different sets of properties that we use for the Gaussian process. First class or first set is kind of calendar information and the current zone temperature. The second set is the field actuators for that zone, or alternatively a kind of lumped value of that information, the HVAC load given as a single value. And third set is the ambient conditions and the occupancy information finally. And we group that into different classes and compared these how the GPA, how the Gaussian process performs on this with this information. So this is the sensitivity analysis. We see first group including in principle all information as a baseline. And if we leave out the field actuator values in the second column and replace them by this lump value of the HVAC load into that room, we see that the error increases significantly. The same is true without the ambient information. So these are values which have to be included into the Gaussian process to get a good prediction. What was a bit surprising was the last column without occupancy. We see that the error does not increase very much if we omit the occupancy. That was a bit surprising for us, but I think the explanation would be since the current BMS system already reacts on occupancy by controlling the CO2 level, this information is implicitly included already in the field actuator values. So therefore, for the comparison, afterwards we use the group without the occupancy information because that is sufficient information to get reliable predictions of the GPR. So here's a performance evaluation compared with the naive GP, so a single GP, and we see that we perform better than a single Gaussian processes with the obtained errors. And this is true for, in principle, all different zones where we tested it. And finally, we also did an annual simulation where we use a whole year as training set and the upcoming year for testing. And this was not possible with a single GP because of the large amount of training data. So this is only done with the log-GP approach, and we see here a quite good error rate regarding the prediction. So conclusion is we have a metadata-driven workflow to configure these models automatically, to just say, I want a prediction of that room temperature, and the GPR is automatically deployed to that room. We have a very good prediction performance, and we've tested this with, as I said, a variety of rooms, and it works there. So what is still open is to validate with different buildings and deploy the models in the real world, and probably look a bit closer in that allocation rule to decide which GPR to use in this log GPR approach. So that's about the presentation. Thanks for your attention, and I'm open for questions.